well characterized. The particles, there are different types of organic inclusions and so on, and particles will not be monodispersed, and it is not a homogeneous system. So we use laponite, which is a very well characterized material. The laponite particles, like any clay particle, they are flat layered structures, and they are nano-sized. The diameter is around 25 nanometers for the laponite platelet, and thickness is very small, of the order of 1 nanometer. This is the chemical formula. And when added to water, the laponite discs become charged and give interesting properties to the solution, which forms a gel at very small concentrations. Now, we have been studying cracks in electric field for nearly 15 years now. And as I said, our first experiment was in a cylindrical setup. This is how, this is the proportion of laponite and water that is taken. It comes to about 0.08 molar. It is stirred in a magnetic stirrer and deposited in a petri dish and let to dry. So this is the circular petri dish, and we used metal foil. We used aluminum foil as electrodes. So we had a rod-like electrode at the center and one around the periphery, giving a circular symmetry or a radial symmetry to the setup. And the pattern depends very strongly on on the direction of the field. When the center is positive, the cracks go like this. They start at the center and go radially to the periphery. But if the center is negative, the cracks start from the outer periphery, which is positive, but they do not come to the center. In fact, they form these arcs, sort of circular arcs around the center. So the patterns are totally different in the two cases. And without any field, the cracks are quite random. So evidently, the effect of the field is quite significant. We have also studied alternating fields. You can see the poster. Shudeshna has a poster. Maybe you have seen it. We also did some modeling of this result using a simple spring network type of model. And these are some of our earlier papers which studied the effect of the DC field, the effect of varying composition. We added some polymer to the laponite, and the crack patterns changed. We also studied the effect of the substrate. If we take glass and we have one type of crack, if we change it to some polypropylene or perspex, there is some difference. And recently, the layer thickness was also varied to see the effect of all these parameters. So now I am coming to the wavy cracks we have observed in the DC electric field. Now, after working with this cylindrical symmetry for a long time, we thought that it would be good to see what happens in the rectangular system. In the rectangular system, the longer edges have the electrodes fitted, one positive and one negative. Actually, why we didn't do the rectangular at first, the reason is that the edge effects become complicated here. In the circular symmetry, there are no free boundaries. So modeling is easier, and the experiment is simpler. But in this case, the effect of these two edges becomes prominent, So we thought we would do it with a long rectangular system and eliminate the edges. This is the size of the system which was studied at first. This is the rectangular box, and this end is positive, this is negative, and the crack patterns are like this. The crack patterns, you can see they are rather quite interesting because they form sort of tree-like patterns. There are large number of cracks at the positive end, but they join in pairs or maybe 3 together, usually 2, and these 2 again join. So it is sort of looks like a bifurcation diagram. We were interested in studying this pattern, but during studying this, Tajkera discovered something very peculiar, so we digressed and started on that new phenomenon which we hadn't thought of before. She noticed that these cracks, they have these peculiar markings which look very regular. Oh, sorry. Here are some more patterns. The marks are not always present. In one crack, there may be marks at one place, but the other rest can be smooth. Like here, you see the marks here, but the rest of the crack is more or less smooth. And on this crack, there are markings all along. Now, in these cracks, often some striation marks are seen. So first, initially we thought that they are the regular, the normal striation marks. But there is a big difference. This work was done earlier, published by Tajkera Khatun. Here you can see a crack tip which is proceeding in this direction. And in this region, these are the lines which are what we call the striation lines, the striation marks, these. And these are actually normal to the crack front. The crack front, the white line represents the crack front. So the striation marks appear normal to the crack front. This is also seen in, this is a nice picture by So Kitsunezaki. For calcium carbonate paste, he observed this, what he calls the plumose structures. These are the plumose lines, and this is the crack front, which is normal. And it is well known that these striation marks are normal to the crack front. But in our case, we found that the cracks are parallel to the crack tip. I mean these lines, the striation lines, they are exactly parallel to the crack tip. And this study has been published, and this is another interesting feature that we saw. This, the advantage of working with laponite is that it is very transparent. So you can see the crack proceeding and you can photograph from outside. So this was photographed from outside the system, and we observed that if you look at the fracture surface, the fracture surface is corrugated like this. It has this wavy nature all along. Now this looks so interesting that we thought it would be a good idea to study this systematically. These photographs are taken when a 100-volt field was applied. So we thought we'd see the effect of the electric field and study this in further detail. What I'm going to show is, suppose this is a fracture and these two segments are being separated. So we can look at the top and look at this wavy contour of the crack, or we can separate the two surfaces and look at this fracture surface. What they did is actually they cut out this portion and placed it normally under the microscope to look at this surface. So this is the lateral view. So here I'm showing the top view of the crack as the voltage is varied. So this is with no field, 0 volt. So there's no electric field here. And this is one particular crack outline. You can see that it is not straight. It has these undulations. And this inset shows that these portions here they have broken off. These parts have broken off. This is for 50 volts. For 50 volts, again, we have these patterns like this. And this is for 100 volts. So you may notice here that as the voltage is increasing, the crack outline is becoming almost a sinusoid, almost a regular sinusoid. Here, it is a wave, but it is not a pure sinusoidal mode.
So let me ask you a question. So your system is made by naponite,
yes,
where there's a charge, and so there is a counterarrier. So you have an electric field inside.
Yes, that is the field of the system itself. I mean, you say that due to the charge on the laponite particles.
No, I mean, you apply a voltage from the center to the boundary, an radial field. But
no, not radial. This is not radial. This is a rectangular system.
Oh, sorry, a rectangular. But you have the two sides,
yes,
with 100 volt difference.
Right.
But in between there is an electron light. And so there is no field inside.
Why? There is an electric field.
Because you have a counterarrier.
Yes.
And also the naponite that is negatively charged. No?
Actually, the field is applied after it has gelled.
Okay, so there is no.
So it is not really fluid. It has started to become. It's not solid, but it is a gel at that time.
Okay, but you say that it is cracking, so it's cracking after.
After, yes. This is what you see in the inset. And for this this breaking off was observed only for 0 volt without any field. But here we see that these edges, they match each other as you would expect in brittle fracture. In brittle fracture, we normally think that the two sides of the crack should fit into each other like jigsaw puzzle pieces. So this is observed here because there's nothing breaking off here. And of course, this is also same for the 100 volt field. And here we are looking at the lateral view, that is, we are looking at the fracture surface. This is again with 0 volt, and this is 50 volt, this is 100 volt. Now here you see that the undulations on the surface, they are not going right up to the substrate. They are coming for some distance, but then they are not going into the, right through the layer up to the bottom. But in the case where the voltage is applied, they go deeper, almost up to the lower surface, the substrate. And they are much more regular than in this case. Here you can see this kind of undulations. They are very deep, close to the surface, but as we go towards the substrate, the amplitude reduces, they become flatter, but still they go much further than in this case. Here are some more pictures. Here again you see that this is where there is no field, and this is the contour you see from the top, and this region, it looks, it seems to be some sort of plastic material in this figure. It also has river lines I'm going to show. And this surface, it doesn't look like a brittle surface. These regions, they look typically like as if the plasticity is there. So this is the case for without the field. Now, we are trying to compile what we have seen and make some sense out of it. Now, when there is no field, the crack contour is wavy, but it is not, I'm sorry, this should be sinusoidal. It is not a pure sinusoid. It may be a superposition of some different waves. And the fracture surface is rough and irregular. So it seems that without the field, the plasticity is more evident. This is a suggestion that maybe the electric field has this effect of suppressing the plasticity in the material, but we are not sure about it. This is just thinking. Now, one question is, what makes the crack deviate from its straight path? Because usually we know that crack, once it starts, it usually tends to go straight without bending or deviations. Deviations mean that there is some sort of instability. Now, in this case, what is making the crack unstable? We could think of two possible reasons, and one is that the instability is known to arise if the crack velocity is very high. If the crack velocity approaches or is at least, say, 40% of the velocity of sound in that medium, then instability has been shown to set in. And this can be one possible cause, and another, this should be two, is it can be due to mixing of modes if it is not a pure mode. Now, in laponite paste, the cracks move very slowly, and they do not move continuously. A crack can move a little distance and then stop for some time and then again go. So it can be easily photographed, and the velocities measured in this way, it is difficult to measure because the velocity is fluctuating very much. But still, if we take some average velocity, it was done from video photographs over time intervals of 5 to 10 seconds, then we found that the velocity of cracks are in this range, 0.05 to 0.5 millimeter per second. There is a large error here because our camera is not very fast, and of course we are taking an average because sometimes the crack is not moving at all. We're trying to look at only the time when it is moving. And if this velocity is comparable to the sound velocity, then maybe we have the reason for the crack deviating from its straight path and leading to this instability. Now, if we compare with the velocity of sound in lapunite paste, now the sound velocity in normal solids is much higher than what it is in this sort of soft materials or paste-like materials. We couldn't do this measurement directly, so what we did was we did some rheological measurements. That is in the poster. Maybe you have seen Shomastri's poster. And from the rheology measurements, if we model the rheology measurements and find out the parameters for the viscous and elastic parts, then it is possible to calculate the velocity of sound. So in that way, the velocity of sound comes to be in the range 2,500 to 3,500 millimeters per second in this frequency range. This is, of course, much larger than the crack speed which we measured. So this mechanism, we can probably rule out that the crack is too fast to go straight and it is deviating. So we are left with the other alternative, and that is mode mixing. This is the usual way the cracks are classified into 3 different modes. This picture is from our book, Desiccation Cracks. Lucas here is one of the co-authors, the first author of the book. The figure is from that book too. So there are 3 modes, as you all know. One is the opening mode. One is the sliding mode, where 2 layers slide on each other. And third is the tearing mode, like tearing paper, where 2 surfaces are going in opposite directions. So it is discussed here and in other places also that if mode 1, this one, mixes with mode 2 or with mode 3, then it is possible to have an instability and have cracks which are bending or wavy. One such example is the 3-point loading experiment. It is very well known. A specimen here is subjected to 3-point loading. These 2 points are fixed and is loaded from the top, and it breaks. And here there is mode mixing in this arrangement. And we have done a similar experiment breaking up perspex sheet. Perspex means an acrylic sheet. So it was manually broken, and this experiment is somewhat similar to this situation of 3-point loading. So it is like this. We take the perspex sheet and just manually bend it and break it. And it was seen that here, along this surface where it breaks, there are very similar markings to what we observed in our cracks. You can see here very clearly that there are marks here. This is a perspex sheet, 0.5 centimeter thick, and these markings are very similar to the marks we found on the desiccation cracks. but why would these two experiments, apparently quite different, how can they be similar? So if you think of this desiccation experiment like this, when the sample is drying, the evaporation starts from the top. So the layers near the top, they are drying faster and shrinking faster. So the stress here in the upper layer is gradually reducing as we are going to the top, because these layers are shrinking much slower. So we can think of this situation as somewhat similar to our breaking experiment. And in that case, then we can correlate those two results where we have those regular markings. Now, what we tried to do is to analyze the contours of the crack to see that what are the different modes present. Because you have seen that without the field, the crack is not a purely sinusoidal mode. Though it has some regular wavy nature, it is not a single sinusoid. But for 100 volts, we got a outline which is almost pure sinusoid. So we did fast Fourier transform of the outline to find out what are the frequencies, or rather what are the wavelengths which are present. Now, the result is like this. For 0 volt, one of those contours analyzed gave this kind of result. Here you see that there are 1, 2, 3, 4 peaks which are quite prominent, which correspond to 4 different wavelengths. And this part you can discard as noise. And at a higher voltage of 50 volt, there are 2 prominent peaks corresponding to 2 wavelengths. But for 100 volt, there is only 1. So apparently, this is just one pure sinusoidal wave. And this was done for a number of specimens for these 3 cases. For this is the original outline, one of the crack contours. It was transformed using image J to this outline, and then the Fourier transform is here. It looks small, but I think you can make out that here there are a number of peaks. And each of these are 4 different cases are shown for each of these voltages. And these are the wavelengths which are obtained. This is for the 50 volt, this is for 100 volt, and this is for the Perspex sheet. Now, these are classified here. For sample number 1, we have this A, B, C, and D. For 2, again A, B, C, and D, and so on. And this is for the 50 volt result. These are the frequencies. Here we have 2 in each case. Here we had 4 in each case. And for 100 volt, we have just one peak corresponding to these wavelengths. For the Perspex, there are a very large number of peaks, and the wavelengths are much less than what we have here. Now, we found that these all these wavelengths, they can be classified into harmonics of only these 3 circled wavelengths. So they are not all independent. If you look at all of those results, then for the Laponite case, whatever the voltage, all of those wavelengths are harmonics of only these 3. And this one has, this is twice of this, this is 4 times of this, and here again this is twice. So these are the wavelengths which were repeated many number of times. And these are the fundamentals. And this one, this wavelength is the one which appeared most often. If we consider all the cases, then the most frequently occurring one, it should not be frequency, the wavelength. The most frequently occurring wavelength was this one, 292.39 micrometers. And all of these wavelengths, they fall in this range, 100 to 300 micrometers. For perspex, these modes are different. There is no wavelength in common for Laponite and perspex. So it seems that the wavelength has something to do with the material, because Laponite, in all cases, we are getting only harmonics of these, but none of these is coming for the perspex case. And these wavelengths are much smaller compared to these. So we thought that maybe the average range of wavelengths for the Laponite cracks, which is quite different from the average range of the perspex sheet wavelengths, can it be related in some way to the plasticity of Laponite? Now, from rheological measurements, I said that it has been modeled by using some standard viscoelastic technique. Only the special feature of our modeling is that a fractional exponent has been used in the equation for the viscous part, that means the dashpot equation. This is a 3-element solid model, and maybe you have seen it in the poster. And from the parameters of the model, which give the best fit to the experiment, we have that the elastic modulus and the viscosity coefficient, if we take the ratio of those two, we get some quantity of the order of time. We get some sort of characteristic time, which comes out to be 1.2 seconds. If we interpret this as relaxation time of Laponite, which is a characteristic of its viscoelastic nature or its plasticity, then a very simple calculation, the velocity of a wave with this wavelength, and if we interpret the inverse of this as a frequency, then the velocity of this wave is coming out to be 0.24 millimeters per second, which is of the order of the measured crack velocities. So maybe we can correlate these wavelengths with the with some characteristics of the system, that is Laponite, in this simple way. So to conclude, I think I'm finishing early. So the conclusions are like this, that in Laponite, we have these wavy cracks, and it seems that when there is a voltage, the wavy nature changes, and for a strong enough electric field, only one wavelength seems to be selected. Whereas for a weaker field, we have a superposition of some different sinusoidal waves. And through this simple reasoning, we can relate the wavelengths for the cracks in Laponite to the relaxation time, which comes from the viscoelastic modeling for the crack velocity. So that is about all. This work was supported by the Department of Science and Technology, Government of India. And Thank you very much for your attention.
Origin of crack formation in the liponite gel by applying an electric field. So why the cracks are forming by applying an electric field in the gel?
Why the cracks are forming?
Yeah.
These are like desiccation cracks. When you look at a field which is during a drought, you see these mud cracks, a similar type of cracks. This laponite is a clay material. It's a synthetic clay, but it is very much like a clay. So if you take some mud and make a paste and let it dry, when it dries, you have these cracks. This is just a similar thing. Is that what you asked? This was your question?
Yeah, the effect of electric field.
Oh, you are asking about the electric field.
Yeah. So
No, why the electric field has an effect?
Yeah.
Is that it? We have not been able to correlate very clearly, develop a theory why the field should have this kind of effect. But the laponite or any clay, when the clay particles are in water, they become charged. Usually they become negatively charged and the counter ions are there. So there are charged particles in the gel which are affected by by an external electric field. Now, when we modeled this system with our spring network model, we made an assumption that the particles are moving towards in the direction of the field. So that is one type of motion of the particles, and in addition, there is also a desiccation. That means we have we can maybe show it here. We have this particles attached by springs. Something like this, and the effect of desiccation is to shrink these springs. So that will produce forces, and if the spring breaks, if the strain goes above a certain limit, the spring will break, and that will be a crack. I mean, if these are broken, then we have a crack here. And in addition, if there is an electric field, these particles will move in the direction of, suppose this is positive, this is negative. So in addition, the particles are also trying to move in the direction of the field. This was worked out for the circular system. So we had the particles moving towards the boundaries and also moving because of the shrinking of the springs. And that could explain our experimental observation of the radial crack and the cross-radial crack. So that is what we could do so far.
The slide of the circular geometry.
The circular geometry that is towards us. Yeah, this one.
So as I can see that there is some symmetry of the crack formation patterns.
Yes,
So,
these are radial.
So my question is, if you shift the one point that at what point you are applying the electric field, if you shift some distance d.
The
so
electric field is electric field is like this. The center is say positive, and the boundary is negative. So this is a strongly inhomogeneous field.
Yes, yes.
The field lines are like this, radial.
If you shift that particular point when
The center.
yes, yes. So
Oh, if we
far from
shift
the
the center towards one
yeah,
Like this you say, we have the center here.
Yes, so then what would happen?
Well, that of course we haven't tried, but we did something like this we did. We had a hemisphere, or a semicircle I should say, a semicircle with positive and this semicircle with negative. And in this case, the cracks came sort of like this, as far as I remember. Not so regular maybe, but something like this. So the effect of the field is there.
Okay, thank you.
Yes?
You were comparing your ripples to the ripples that can be seen in perspect fracture. I remember in mode 1 fracture in PMMA, when you have a fragile interface, the type of experiment that Daniel Bonamy was showing, some that were done in Oslo and studied there. Very typically, there are lines which correspond to the crack front that remain behind the crack path, and these white lines appear when the front is pinned. And when the front passes fast, there's no line. So you can see you can see the history of you can read the history of the crack front motion on the white lines you have. And if you wait for very long and your system is not too much loaded, sometimes some of this line actually transforms into a sidewise crack that just breaks one of the side plates, which is open. These lines seem to correspond to accumulating damage that penetrates on the side when the front is pinned for very long. So in your case...
that is the mode 1, you are saying?
That's a mode 1 fracture between two plates, yes.
Okay, so just opening like this.
Opening like this, and there's and there are pinning. I mean, there's a sandblasted surface, and then it's fused again. So the result is that you get a heterogeneous GC landscape, and the front stops and goes. And when it slows down a lot, it leaves some white marks that you notice. So I was just wondering in your system if the crests that you see corresponds to periods where actually your rupture front is pinned, and then it accelerates and deviates, and whether your crests are correlated with the crack front speed.
Probably that would be the what I was referring to as the usual type of what is it called? Striation marks. This one.
No, it's no. The white lines. I mean, you were showing some other perspex things where the lines you had corresponded to the crack fronts. What I'm talking about is a situation where indeed the lines that remain on the PMMA plates are corresponding to some instantaneous positions of the front. And when the front doesn't go fast, there is a marked line that stays on the surface when it accelerates afterwards. So at least in PMMA, which is driven in subcritical growth with spinning centers, what we observe is these lines that correspond to the front when it's pinned. And then if you have an instability in speed, if the system, like how gamma depends on V, drives you an instability from going slow to fast, you can then have something that leaves
I think
lines.
To understand that, we should try to do the perspex experiment in mode 1. Is it?
Yes,
because we are saying that this is mixed mode, it is bending.
Well, no, the experiments I was talking about now are mode 1 experiments. Yeah.
But we haven't done mode 1 actually. We are bending it rather like that 3-point loading experiment. So we are trying to correlate with the drying case. But drying case is not really mode 1.
Yeah, you have several modes. But if you see the speed of your front, you can try to see if when it goes slowly, it leaves a mark, and when it goes fast, it doesn't.